Hi, this is my video number 6 for differential equation. In this video I'll talk on autonomous system. So in general we have a system of equation. We have x, this is x dot, this is a system, is equal to f x tx or xt or tx. So you can look at this system as like x 1 dot equal to f t x1 x2 and so on. X 2 dot as f t x1 x2 and so on. So this should that's like f1 f2 and so on. So you have xn, this is fn t x1 x2 and so on up to xn and so on. Okay, so this is we call as a system of differential equation of order 1. Now if f, this the right hand side f tx equal to gx, which is does not depend on x, does not depend on x on t, sorry, then we say the system, this system. So let's denote this as a star. We say that system is an autonomous system. Autonomous system. Okay, for example, if you have that system x dot is equal to negative 5x plus 2y, and y dot is equal to x minus 4y, where of course x is a function of t, y is a function of t. So in this system, the first equation we don't have t explicitly, as well as the second system we don't have t explicitly. So this system we call it as a autonomous system. So now if g, we have if g, our autonomous system, if g, and the differentiation of g prime x for each x, I think I better write like del g over del xi. If this is continuous in D, so that's continuous in D for any specific domain, then by the uniqueness and existence theorem, given any epsilon, given any point, say t naught eta, where eta in D in our domain, then there exists a unique solution phi of t such that phi t naught is equal to eta. Okay, so if we observe the linear system, for the linear system, with constant coefficient. So we have x dot is equal to ax. Yeah, this is a system. So we have x bar, means we have x1, x2, x3, x4, and so on, as well as x here we have x1, x2, x3. So we have a system here. So in this case, for the linear system with the constant coefficient, so this we call it as a autonomous system. Why? Because it's not depend on t. Now if you consider two-dimensional autonomous system, where x dot equal to p xy and y dot equal to q xy, where xt and yt are unknown, unknown scalar function, and pq and pq, and as well as del p, del x, del p, del y, del q, del x, del q, del y, are continuous. Then the existence and the uniqueness of the solution are guaranteed. Then the existence and uniqueness of the solution are guaranteed. So which means that if we have the autonomous system like that, two-dimensional autonomous system, where p and q are continuous, if we differentiate p with respect to x with respect to y, and differentiate q with respect to x and with respect to y, all those are continuous, then by the existence theorem said that this system has a unique, and the solution exists and the solution is unique. Okay, so now let us see some of the theorem that related to that system, the autonomous system. Let me call that system as a double star. Okay, let me call that double star because I'm going to refer to this system later on. Now look at the lemma 411. Lemma 411. If xt and yt for t between a and b, is a solution of our autonomous system, which is double star, then for any real constants, for any c, a real constant, then the function x1t is equal to x t plus c, and y1t is equal to y t plus c. So what we do here is we do the translation. Yeah, we do the translation. So if this x and y are solution to the system, then if we do the translation to the those solution x and y, and we name it as x1 and x2, x1 and y1, so then this x1 and y1 are also the solution to our system, autonomous system. Now, how do you prove this? Proof isn't difficult. We can consider x naught t as x dot t plus c. Okay, and we know that our system is x t is equal to p xy, yt is equal to q xy, and y t x and y are function of t. All right, so if you have this x1 dots, we differentiate that, so means we differentiate that respect to t, so we have x dot t plus c. So, and our x dot, this is x dot y dot. Okay, then we have x dot t plus c. We can use this where x dot is p x y, so we have here is p x. Now x function of t plus c, y function of t plus c. Okay, and we know that x plus tc, x plus tc, and x t plus c, y t plus c, which is this. So this is equal to p x1t, y1t. Yeah, so it means it's a solution to our autonomous system. Also, we can do the same. You can do the same as well as similarly for y1 dot. For y1 dot, we got x q x1 t, y t. Okay, so this show that x1t and y1t solution of our autonomous system double star, and clearly is defined for t between a minus c, b plus c. And this lemma is applied for higher dimension autonomous system, which means not just consider x1 and x2, even if you have sum of function, let's say x1, x2, x3, x4, and so on, and which as long as satisfy that, yeah, so which means the translation is also the solution to the our autonomous system. Okay, so what about for the non-autonomous system? Does it apply this property? Yeah? For the non-autonomous system, for example, we may consider x equal to x and y dot equal to tx. Yeah. So the solution is given as x equal to et, y equal to et minus et. Yeah. So if we let x1t as x plus tc, x t plus c, and y1t as y t plus c. So we can see that from there, for x should have no problem because our x not depend on t, but for y depend on t. So we have y1 dot t. This is y dot, yeah, because that's we dot there. We differentiate that with respect to t plus c. Okay, and y dot t plus c, which is the solution is given, our equation given as that. So this is give you t plus c x, and x is a function of t plus c. Okay, and of course from there you can split this. This give you t x t plus c plus c x t plus c, and this give you t, this is x1 of t plus c x1 of t, which is different than t x1 t. So what we can say from here that those lemma only apply for the autonomous system but not for the non-autonomous system, except for c equal to 0, yeah, unless for c, or except for c equal to 0, but which is this is not the case that we consider for, because if c equal to 0, then there is no translation. Okay, now we look at the what we call if the solution, yeah, x equal to xt, y equal to yt, what can you say about this solution? Xt is a function of t, y is a function of t, so which means we have a kind of a curve in a certain domain D. Yeah, so that curve we call it as a trajectory, or the characteristic of the autonomous system. Yeah, so let x equal to xt and yt be the solution of our double star, the autonomous system. Then as t varies, the solution which is x t yt describe a curve lying in D. So this curve we call it a trajectory. Yeah. Okay. Now we are going to see some properties of of the trajectory of the curve, a solution to the our autonomous system. Yeah, look at it. We have lemma 4.12. Through any points, passes at most one trajectory. Yeah. So through any points passes at most one trajectory. So if you have, let's say this is your domain. Let's say that's your domain. You have a point. Let's say this is your point somewhere there. Okay. Then the trajectory. So this point somehow must lie on the trajectory of the solution. If you have a point there, we also have the trajectory there. We also have a trajectory for that point, and so on. Yeah, for any points, so we have at most one trajectory, at most. So to prove this, so we let's say we have two trajectories, say C1, where x equal to x1t, y equal to y1t, and C2, x equal to xt2, y equal to y2t, be trajectories having a common point. Yeah, let that be trajectories having a common point. Okay, and those common points are, say, x0, y0, where x0, y0 is the x1, t1, y1, t1, x2, t2, y2, t2. Okay, x0, y0 is equal to x1, t1, y1, t1, x2, t2, y2, t2. Where t1 is different than t2. So if t1 equal to t2, then in that case the uniqueness is contradict with the uniqueness theorem. Yeah, the uniqueness of the solution. So from the previous lemma, from lemma 4.1.1, the previous lemma, if x, y is a solution to our autonomous system, then if we do the translation, then those translation is also the solution to the our autonomous system. So we have, since xt is the solution, so x, if we take x equal to x t plus t1 minus t2, where t1, t2 is our c, yeah, yt equal to y1 t plus t1 minus t2 is also a solution, of our autonomous system, double star. And we have x t2 y t2, this is equal to x1, this is should be x2, y2 t2, x1 t1, y1 t1, this is equal to x0, y0. Yeah. So which means C1 and C2 are coincide. So if you have, so this lemma says that if you have a common point, let's say x naught, y naught, yeah, and then the trajectories which passing through this point x naught, y naught, we only have one for one system. We only have one trajectory passing that point. We cannot have this. Let's say that point. We have the trajectory there. We have another one there. We have another one. So this cannot happen. Yeah. So you can imagine like yeah, I think you have learned at the school level that the magnetic field. Yeah, the magnetic field. In the magnetic field, you have north, south. So we have those things. The electric field, the magnetic field. Then this line, what you call that, this magnetic field cannot across each other. Yeah, so you cannot have something like that, and another one suddenly another one coming like that. So you cannot have this thing. So in this case, if you have a particular point here, so this particular point only passes by that trajectory, not by that and not by the others. So this is what we mean by this lemma. Okay. Now I would like to go to the categorize of the trajectory. We have a stable trajectory, we have unstable trajectory, and before that we need to find the critical points and so on and so forth. For that, I think I'm going to give in the next video. For this video, I think I just introduce you what is the autonomous system. Yeah, introduce you what the autonomous system, and as well as some of the properties of the solution of the autonomous system. Yeah. So with that, I thank you.